In this video, we'll concentrate on vector product or the cross product between two vectors. Suppose you're given two vectors a and b as shown. The vector product between a and b can be written as follows: a cross b equals to c, where the magnitude of vector c, which is the magnitude of a cross b, is given by the magnitude of a times the magnitude of b times sine of the angle between them. Now, the direction of c is as follows. C lies in a direction perpendicular to the plane containing vectors a and b. So it could be this way or that way. Now, which one is the right direction? The direction of vector c is given by the right-hand rule. Now, what is the right-hand rule? Now, you simply curl your right-hand fingers from the direction of a to the direction of b as shown by this arrow. So that means you curl your fingers like that. Now, the direction of your right-hand thumb, which is that, is the right direction for vector c. So that means vector c is given by that arrow. So that is your vector c. What happens if you reverse the order of the vectors in the vector product? So now we take b cross a. Now, what is the answer to b cross a? Now, the magnitude of b cross a can be shown to be the same as a cross b, because b cross a is given by magnitude of b times magnitude of a times sine of the angle between them. So it is the same as the magnitude of a cross b, or what we called magnitude of c earlier. Next, let's determine the direction of b cross a. Using your right hand, when you curl the fingers of your right hand from b to a as shown by this arrow, or like that, you see that the direction of your right hand thumb is pointing downwards. So that is the direction of b cross a. And since the magnitude of b cross a is the same as the magnitude of a cross b, which is the magnitude of c, and it's pointing in a direction opposite to that of a cross b or c, then b cross a must be minus c. So we label b cross a as shown. So that is minus c. So b cross a is minus vector c. Now let's assume we are given two parallel vectors, x and y. What is the cross product of these two vectors? Let's say x cross y. Now, since these two vectors are parallel, the angle between them is 0 degrees. And we know sine of 0 is 0. Now that means the magnitude of x cross y is 0, which implies the cross product of x and y vanishes. So the result is cross product or vector product of any two parallel vectors is 0. Now let's apply all the things that we have learned thus far to unit vectors, the three unit vectors that we are familiar with. Now let's say we want to take a cross product of I and j. I hat and j hat. Now the angle between them is 90 degrees. So the magnitude of I cross j is the magnitude of I times the magnitude of j times sine 90. So that means you get 1. Now what about direction of I cross j? Now if you curl your right hand fingers from I to j, you will notice that your thumb will point in a direction of positive z of z-axis. So the vector that satisfies the condition of being 1 in magnitude and points in the direction of positive z or the z-axis is the k hat vector. So we conclude that I cross j is k. I hat cross j hat is k hat. And reversing the order of this vector product, j cross I will be minus k hat. By proceeding in a similar manner, we can now construct a table of vector product involving different unit vectors. So let's rewrite what we have just found. I hat j hat equals k hat. Next, j hat k hat equals I hat. You should be able to convince yourself that this is the case by using the same argument that we used for I cross j equals to k. The third is k hat cross I hat equals j hat. Now, if we reverse the order, it will pick up a negative sign. So j hat cross I hat is minus k hat. K hat cross j hat is minus I hat. I hat cross k hat equals minus j hat. And finally, cross product of I hat and I hat. Now these are considered to be parallel vectors. So we have shown before that cross product of two parallel vectors will vanish. So I cross I is 0, j cross j is 0, and k cross k equals to 0. Now we can use these results to determine vector product or cross product between any two generic vectors, as we shall see next. Now in this example, we have two vectors a and b, and you want to take the cross product of this a and b. Now a and b are both expressed in I hat, j hat, and k hat form. So let's do term by term. First, I hat and j hat, we know that to be k hat, but then you have 3 and minus 1 there, so that's going to give you minus 3k hat. Now likewise, I hat and k hat, that's going to give you minus j hat, so together with the 3 you'll have minus 3j hat. Next, the second term, j with j, that's 0, j with k, that's going to give you I hat, with the 3, that will be 3i hat. And finally, k with j. So k cross j is minus I hat, but then you have a minus 2 and minus 1, so that's going to give you 2. 2 times minus I hat is minus 2i hat. And then k with k, that's going to give you 0. So when you add all these non-zero terms, you're going to get minus 3k hat minus 3j hat plus 3i hat minus 2i hat. And the final answer is I hat minus 3j hat minus 3k hat. So that's the final result for this. vector product. We can also evaluate the same cross product using determinant. So first, you write down or you list the components of vector A on the top row here, followed by components of B on the second row, because we are evaluating A cross B, so the order matters. So let's first evaluate the X component of this vector product. Now the X component of this vector product can be evaluated like this. So you cross out the I hat in two mutually perpendicular directions. So you're left with 3 minus 2 minus 1 and 1. So now you proceed like you're evaluating a 2 by 2 determinant. That means 3 times 1 minus 2 times minus 1. So it's going to be 3 minus 2. Likewise, the Y component can be evaluated in a similar manner. Note that I have already placed a minus sign here. It's just part of the formalism. And you cross out the J hat in two mutually perpendicular directions. That would leave you with 3 minus 2, 0, 1. So if you evaluate that 2 by 2 determinant, it will be 3 times 1 minus 0 times minus 2. So 3 minus 0. Finally, the Z or the Z component plus K hat. So let's look at the K hat. You cross the K hat out in two mutually perpendicular directions, and then you take the determinant of the 2 by 2 determinant out of 3, 3, 0 minus 1. So 3 times minus 1 minus 0 times 3. So that's going to be minus 3 minus 0. Final answer is I hat minus 3J hat minus 3K hat, as what we have obtained before. Another example, cross product of B and C as shown. So we can do term by term as before. J hat and I hat. So J hat and I hat will be minus K hat. But you have a minus sign here, minus 1 and minus 5, so that's going to be 5. So together that will be minus 5K hat. Next, J and J, that's going to be 0. And then J hat and K hat, that's going to be I hat. You have a minus 1 here, minus 1 here, so that's positive 1, and together they give you I hat. Finally, K hat and I hat, that's going to be J hat, but there is a minus 5, so it's minus 5J hat. K hat and J hat, so that's minus I hat. And followed by K and K, that is quite simply 0. So when you write down all these non-zero components, you have minus K, 5K hat, minus 5J hat, minus I hat, and plus I hat. So your final answer is minus 5K hat minus 5J hat. So that's the answer for this vector product. As shown before, we can also do this same cross product using the determinant way. So the X component can be found by crossing out the I hat in two mutually perpendicular directions. So that is 1 minus 1. And then now the Y component, crossing out the J hat in two mutually perpendicular directions. So that's 0 minus minus 5. And finally, the Z or the Z component, which can be obtained by crossing out the K hat in two mutually perpendicular directions. So that's 0 minus 5. So the final answer is minus 5J hat minus 5K hat, as we have found before. Thank you for watching.